B2, this question is about the wave nature of matter and quantum energy states. Describe what is meant by de Broglie's hypothesis. Now notice it's 2 marks, so you've got to put enough information down to get those 2 marks. Now, de Broglie's hypothesis is basically summarized by that formula over here, so that your wavelength, the wavelength of any particle, any particle can be an electron, proton, anything, a human, is equal to the Planck's constant divided by the momentum of the particle. So that's what de Broglie said. He basically said, and this would be the other mark, would be that every particle has wave-like properties associated with it. In B, it says an electron is confined to one dimension in a box of length L. The de Broglie waves associated with the particle form standing waves in the box with wavelengths given by 2L over n. For those that did higher level, you should remember that, where n is equal to 1, 2, 3. N is a natural number. Show that the energy levels En for a particle are given by this formula over here, which is over here. So basically we are proving that formula there. Okay, so in doing this, we are basically going to be using this formula over here, that P is equal to H over lambda, but we want kinetic energy. So I want to somehow put my momentum in terms of kinetic energy. Now we remember our formula for kinetic energy is equal to a half mv squared, and therefore I can say that Ek is equal to m squared v squared over 2m. I hope you will see that that is the same, that these two are equivalent, that this is equivalent to that, just obviously the half down to the 2, and I'm dividing this m squared by m. I've still got my m there. Now this, because your momentum is equal to mv, I can say that Ek is equal to p squared over 2m. Now going to this formula over here, P is equal to h over lambda, I have that my lambda, my wavelength, is given by 2L over n. So I'm going to divide h divided by 2L over n. Remember, when you divide by fractions, you invert and multiply. So that's going to be nh over 2L. And I can put that in, this is P, into this equation, but I've obviously got to square it. So I'm going to get n squared h squared over 4, 2 squared, L squared, and that goes into my formula for E, and I put in an n substitute because I've got this n here, and that obviously all gets divided by 2m, so I've still got my 2m there. So I get n squared h squared over 8ml squared. So I have given that. Now that gives the energy of an electron at a specific energy level. This n is your natural numbers. E is equal to 1. N would be the energy level 1, energy level 2, and so forth. So it says the energy for this question over here, question C, the electron makes a transition from the energy level energy state given by n is equal to 4 to n is equal to 2. The length is given by 1.3 times 10 to the negative 9 meters. Calculate the energy of the photon emitted. So what's happening here, if I go to this over there, let me just clear this. So I am looking at this situation over here where n is equal to 4 and n is equal to 2. It drops down, my electron drops down. Now n is equal to 4 is going to be, according to this formula, will be Ek is equal to 4 squared h squared 8 the mass of the electron and the length squared. So this would be for E4, and you have your E2 would obviously equal 2 squared 8 squared over 8 MEL squared. And the energy that is given out here, this energy that is given out in the form of a photon, would be the difference. So it would be E4 minus E2. It would be the difference in the energies. So basically everything that's the same, that's the same, that's the same. The only difference between the two is that. So when I work out that difference, the energy of the photon, it's just going to be E, and that's going to be the 4 squared, which is 16, minus the 2 squared. So it's going to be 16 minus 4, which is 12. And then we're going to have our h squared, which is 6.63 times 10 to the negative 34. And that's h squared. Don't forget to square the whole thing. And then it's going to be divided by 8. The mass of an electron, we get that from our data booklet. That is 9.11 times 10 to the negative 31. That's not squared. But then we multiply by the length, and we're given the length. That is your 1.3 times 10 to the negative 9. Times 10 to the negative 9, and that is squared. So we put that all into our calculator. So let's do that. Let's put that in. So we're going to have our open brackets here. I'm going to get 12 times 6.63, and this is where it's important to use this way of writing it. It's to the negative 34, and I'm going to square that whole thing, squared, like that. And that square will square the 6.63 and the 10 to the negative 34. And I can close my brackets around that because I want it all to be divided by this bottom part over here. So I'll open another brackets. So that's going to be 8 times 9.11. Again, I use my there, and I'm going to get negative 31 times my 1.3 exponent negative 9 squared, and now I close my brackets and I push enter, and I get an answer there, 4.28. and you see you've got obviously a lot of significant figures there. We were just given 2 significant figures there, so I'll write my answer to 2 significant figures. 4.3 times 10 to the negative 19, and that will obviously be in joules. Then it says, after that, it says the wavelength. So let's just give ourselves some space here. So let me just write that again. So we've got the energy of this is 4.3 times 10 to the negative 19 joules. We want to know the wavelength. So we obviously go back to this formula over here that we're going to use. We have got our energy is equal to HF. So I'm going to get my energy, which is 4.3 times 10 to the negative 19 is equal to HF. But I'm looking at the wavelength, so I'm going to write it like this. 6.63 times 10 to the negative 34 times your speed, which is 3 times 10 to the negative, to the 8, not negative 8, divided by my wavelength. And so wavelength is going to be this divided by that. So let's check that out. Let's put that back into my calculator. So we're going to clear. I'll also clear that. So we're going to get 6.63 my exponent, and it is to the negative 34. Negative 34 times 3 exponent 8 divided by 4.3 exponent minus 19. Enter. And I get an answer there of 4.625 times 10 to the negative 7. Again, I'm going to do two significant figures, so it's going to be 4.6 times 10 to the negative 7. And obviously, because we're looking at wavelength, we're looking at a length that is going to be meters.